All right, recording is rolling. Welcome to Tuesday, October 10th. I have a demo lined up for you guys. We're gonna knock out the rest of the chapter 6 textbook questions. And then I got a lab lined up for you guys with the turntables. You guys got turntables on your desk. And so some reminders. The first 9 weeks is about to come to a close here in a couple of days. Check focus, make sure you have everything turned in all your classes, including this one. Guys, anything you don't get to me, if it says NTI, like rolling into this weekend, at that point, there's just nothing I can do about it. Like once grades are in, it's like pretty much impossible to change. Like right now, I can just go in and flip it in any grade. So whatever, right? If you're missing something, I can just put it in, right? But like 1 week from now, or I won't be able to do that. So check focus, make sure you got all your stuff in. Tomorrow we're going to start universal gravitation. I'm treating that as part of the same unit that we're doing now, so it'll be all in the same quiz. Which is what we're doing. We're going to take gravitation starting tomorrow. We're going to find out with this rotational mechanics and make orbits. Right. So yeah, where we are. All right. I think it was yesterday. Did I show you guys this? Oh yeah. Oh yeah. Right. I think yesterday I showed you guys this. Is that right? Right. So there was a textbook question that had to do like a car go around a curve. Now, if it was a flat track, suppose the road was flat. If it's flat, what kind of force allows the car to make a turn? Yeah, friction force, right? Can the car make a turn without friction? Well, if the road is banked, it can, and that's what you guys are seeing here. You guys remember, there's only two forces I'm showing on this car. It's weight and a normal force from the road. Notice I haven't actually drawn friction. Okay? That might correspond to a specific speed. Like if you know the speed limit and you know the radius of curvature of this road, you can calculate or you also know Earth gravity. You can calculate the angle you have to make the road, right? Or, well, I guess if you know any three of these, you can solve for the fourth one. Right? I think I walked you guys through this proof yesterday, right? Hey, how about this? What if the road's already built? So you see its radius of curvature, you see the bank angle. Do you think you could calculate the speed you have to go so that you can make the turn without any friction? Right? Let's see what that looks like. What does that look like? Flip over here. Classic physics question right here. Here we go. Yeah, you guys see those motorcycles going around? That is a really steep bank right there. Ooh, that's almost over the wall. Not quite, but it's getting, it might be like, what, 70, 80 degrees to the horizontal? Ooh, that's a real steep bank. Could you imagine if those motorcycles going a little bit faster, they kind of tend to drift up the wall? I think they slow down, but kind of tend to drift down, sort of, right? But there's like some constant speed they're going. They're not speeding up or slowing down. Some constant speed. Notice I'm not saying constant velocity because they're on a curved path, so their direction's changing. Right? But the radial size is also constant, pretty much. Right? Sometimes you hear the phrase dynamic equilibrium because constant speed, constant radial size. Right? But it's not true equilibrium because they're on a curved path. Right? There's a net force on them, like a centripetal force. Now, when that car goes up there, guys, are those cars more massive than those motorcycles? Right? So when the car goes up there, is it going to have to go faster, slower, or the same speed as the motorcycles? The same speed? Well, let's see what the video says. Ooh, are those cars going the same speed as the motorcycles? Yeah, they're on the same speed. Let's go back to this proof and check out. Wait, what is the mass net? Oh, guys, do you see mass anywhere in this Boxton expression? No. Right? I mean, it was part of the setup, but it canceled out right here. Canceled out. Yeah. So if you had like a whole line of vehicles, little motorcycles, little cars, big trucks, yeah, they all have, yeah, it's the same speed they need to go to turn without friction on it. All right, that's kind of. Let's do these textbook questions. Are we on number 60 what? 66 right now? Right. Carnival clown. Right. Carnival clown. Rides a motorcycle down a ramp and around a vertical loop. The loop has a radius of so many meters. What's the slowest speed the rider can have at the top of the loop to avoid falling? 65 minutes first. Okay, let's do 65. Friction provides the force needed for a car to travel around the flat surface track. What's the maximum speed the car can travel? Radius of so many meters and friction such. Okay. Number 65. Maybe it's good that we're hitting this one. Yeah, I think we're off a little bit on the time because this is actually kind of similar to the turntable lab we've been having you guys today, with a couple of differences. One difference is this car is like a point mass going around So we're going to use some version of like mv squared over r for centripetal force, just like your guys' centripetal force lab with right? Versus the turntables, maybe like a rigid disc. Here, instead of, I'll bring up the expressions. Instead of doing this, which mv squared over r, which we're about to do for this particular question, right? Maybe you could substitute in omega times r here for v and get like this rigid disc turning, like a turntable version, right? It's the same thing, just a different perspective, like for angular velocity. The other difference is I'm going to have you guys find what is the coefficient of friction later today between two surfaces versus here they gave it to you. It's they gave you coefficient of friction, they asked them for speed. Okay, right. But otherwise, there's definitely a conceptual crossover, 65, between this one and your guys' lab later today. So flat circular track. Right. Maybe here's the center of the circle right about there's. Right, car. Right. Here's the radial size right here. Call it R for radius. Okay. Now from above, so we're up in a helicopter aerial view. Look down. Look down. Right. I see one force on this car. Okay, so this here, this car has a speed, has a velocity. It's going straight forward, v velocity. Right? Except it's also turning. It's on a curved path. You guys see it's on this curved path next. Okay. So which way does the friction force point? How about to the left? Right, force friction. Right. So as the car moves forward, the friction between the tires and the road forces it to left. Letting it make a left-hand turn. Okay. What about from behind the car? Look at a different perspective. Here's the car from behind. Tail lights, license plate, rear view window, rear tires. Right. There's a car from behind. Right. Let's do a free body diagram from behind. I bet this car has a weight, a normal force, and then the friction force, sub FR, that's letting it make the turn. Right. I think I got a poster hanging somewhere around here that shows like these two side by side, two different perspectives, the same scenario. Right. So I'm thinking the setup is going to be that this friction force is acting as the centripetal force. Right. That's what's going to kickstart this whole process. Right. The centripetal force is provided by the friction force. Right. That's the framework. Everything else is going to follow from that. Right. Is that all right? Right. That friction force is acting as the centripetal force. Right. Now, your guys' lab, there was a tension in the string that was holding a Play-Doh canister in a circle. And that tension string was weight. Right. Right. So what do I need to substitute in for centripetal force? What expression? Right here. mv squared over r. Right. mv squared over r. Right. Oh, I see the car. Oh, wait a minute. The car has some mass. They never actually told us the mass of the car, did they? Ooh. Do you think that's a hint that's probably going to cancel out somewhere along the line? Right? I think it's going to cancel out. Maybe we should look for that. And if you think it's really confusing and you really need a mass, I bet you could just make up a mass. And if it works universally, then it should work for any mass car. Right? We got a speed, which we're actually solving for. They said, how fast can the car go? So ultimately, we're solving for that. And they gave us a radius of curvature. Right. Friction force. Let's go back a few weeks. Friction force is equal to what times what? Has to do with these two. How is friction force related to normal force? Through the coefficient of friction, right? Right? Isn't coefficient of friction the ratio of these two? So friction force, I can rearrange it to get coefficient of friction times the normal force, right? That's what friction force is, coefficient of friction times normal force. Right? Well, it's equal to that if it's kinetic friction. Actually, I want static friction, don't I? Because I don't want the car to be like sliding off the road. It should be static friction, right? But since we're maxing out the speed, we're saying like if the car went a smidge faster, it would break friction slide off, right? Even though this is static friction, and I usually use an inequality sign here, I can go ahead and say equals because I'm like maxing out the possibility of like how fast can it go, right? One more substitution. The normal force is also equivalent to the what? The weight. You guys see that? So can I substitute that? Bam, right there. Right, let me go do that. So mv squared over r, solve for v, is equal to mu coefficient of friction times mg. Okay. Oh, now what cancels out on both sides? The mass. Oh yeah. So you could pick it in the car. It doesn't matter. You pick a little motorcycle, pick a big freight car. Doesn't matter. You know what? We're real close to solving this in terms of variables. I mean, you guys can plug in numbers whenever you want. But could I just cross multiply this r and then take the square root and just get a general answer? Right. So b squared is mu times g times r, and then take the square root. Coefficient of friction times gravity field times radius of curvature, like that. Because right. And now you can just plug in whatever numbers you want. Here, let me make up some numbers. Let's say that the gravity field is about 10 meters per second squared. We usually use. Let's say coefficient of friction is like 0.9. Let's say the radius of curvature is like 11 meters. How about that? Okay. So going 0.9 right there. I'm going 10 meters per second squared there. I'm going 11 meters there. Right, now my numbers are different from your book numbers, but I mean it's all in terms of variables, so everybody's the answer, right? Right. Let's see what this is. Square root of that times that times that times that, all grouped together in that radical. Okay. I'm looking at 9.9499. All right, so that's meters per second. Right, that's how fast it can go. My car is made of that. Right. Okay. So if it goes any faster than that, it's gonna break friction and slide off the road. If it goes less than that, then it's safe. Right, but this is like right at the breaking point. Right? You guys ever driven off the interstate and you make that tight curve? And you're like, ooh, maybe I'm going a little too fast. Kind of tap the brakes. Oh, okay. Or not. Okay. Glad to have you here with us. Oh yeah. Yes. All right, 66. Carnival clown time. Riding a motorcycle around this loop. What's the slowest he can go without falling off the loop? Let's give him a loop going right here. All right. Here's our carnival clown. Go around. Carnival clown right there. Right? Hey, he's got some instantaneous speed right here. I call it V. Right? In fact, he better, right? Because what if here, here's a radius right here, right? What if he's not moving right at that point? What if he goes to runs out of steam? What's he gonna do? He's gonna fall off. Oh, solid clown. He's gonna fall off the track. Right? Now, what if he's going real fast? Like zoom, he'll easily whip around, right? But there's like solid braking power. You know what this reminds me of? Does this remind you of? Remember, I filled this cup with water and I would fly it around in a vertical loop, and I was throwing the question to you guys like, like what's the slowest I could get the spinning so that the water like stays in the cup, like upside down, right? There's goldfish swimming around, doesn't fall out, right? Hey, that's probably like exactly this question too. I bet it's the same question, sort of. Hey, frame relative. Let's do a free body diagram of this this clown right at the top of the loop. What's one force that's definitely acting on this clown? Yeah, it's weight, mg. Right. Now, suppose it gets around with like sufficient speed. Sometimes you'll see that phrase. Maybe you see this problem in college and say sufficient speed. In that case, there would also be what kind of force acting on the clown? Normal force from the track, pointing which way? Straight down. Normal force, right? Is that right? And I could say, and now that's not exactly what the book is asking, but I just want to give you guys a bigger picture of what's going on, right? That could be happening, right? Sufficient speed gets around. That those two forces are acting together to keep this clown on this curved path. That means they're acting as a centripetal force. Can I say centripetal force is provided by the combination of both the weight and the additional normal force from the track? That's what that would be, right? Right? Now, your book says, hey, what's like the minimum speed it takes to get around? Now, if it's minimum speed, it just barely gets around. Let's say it makes this loop like 10 different times. Every time it goes a little slower, a little slower, a little slower. What's happening to this normal force every time it goes a little slower? Gets a little smaller? If he just barely gets around, then what's the normal force equal to? Like 0? It's going to approach 0? So we're just going to get rid of that guy. And we're going to say the only force that's keeping this clown on a curved path right at the top for that very instant is his weight. And this one, we're just going to let go to 0, like 0 newtons. We're just going to get rid of it, right? Right, that's it. Okay. So, what's a good expression for a centripetal force for the scenario? It's the answer to your lab. Who sees it on a poster up here? Looks like your lab. MV squared over R. Oh yeah. Yeah, you guys remember that. In this case, it's provided only by this clown's weight. Ooh, what cancels out of both sides? Yeah, the mass. The mass of this clown. Notice they never actually gave you the mass of this clown. And it doesn't, or motorcycle, right? But it didn't matter anyway, right? Got fat clown, skinny clown, right? No matter. Right? We're solving for what is the speed, and this is like the minimum speed because we let the normal force go to 0, right? Hey, you know what? We can solve this one in terms of variables too, right? Are we just 2 steps away? Right, or you guys can plug in numbers whenever you want, but in general, we're gonna cross multiply the r and take the square root. So b minimum squared is equal to g times r. Therefore, b minimum is the square root of gr. Right? That's the same solution as the water in the cup. When I was spinning this around, plugging 10 meters per second here, or sorry, 10 meters per second squared here, and you know the radial size. You guys take the string as some like a radial size of that curve, right? You can figure out how fast this had to be going, like meters per second at the top, right? Let's plug in some numbers. What numbers do they give you? Really only need those 2, right? Yeah, they only explicitly give you one number. I'm gonna say the radius is let's go 9 meters. Okay, and I'm allowed to know what g is, about 10 meters per second squared. Okay. So for me, for my clown, that's gonna be square root of 10 meters per second squared times 9 meters. The square root of 90 is square root of 90. Looking at 9.49 meters per second. Right? So if he goes that speed, he'll just barely get around. If he goes like 10 meters per second, okay, it'll be a little bit safer. If he goes like 9 meters per second, oh, fall off the track. No. Okay. You guys get that? All right, one more. Number 74. Ooh, here's a fun one. It's a multi-part, but this one's fun. Early skeptics of the idea of a rotating Earth. Because at one point it was actually debate, right? Well, what's the shape of the Earth? Is it shaped like a ball? Shaped like a pancake? So that the Earth spinning would throw off people at the equator into space. The radius of the Earth is so many kilometers. Ooh, do you guys think we probably want to convert to meters? Point probably. Show why this idea is wrong by calculating the following, right? And then there's multiple parts to this. They give you a person so many kilograms. What's the speed of somebody at the equator? The speed of somebody. So we'll do part by part. Figure this out. Let's go. 74. All right. Oh, back up. You guys can see this. Yeah. All right. Here's the Earth. We got equator, North Pole, South Pole. Right. Do you guys remember I was talking about the Coriolis effect about a week back? Right? I was saying everywhere on Earth has the same angular velocity, like radians per second, right? Turns per second. But depending on your latitude, different linear velocities. So if you're up here on the North Pole, then you're not moving any like linear speed relative to the spin of the Earth. But if you're down here on the equator, you're moving pretty fast. And the first question, in fact, is, well, how fast are you moving, right? And is it going to throw this guy off the Earth? And if it doesn't, then how close would it be, right? So, yeah. I bet we have to figure out what is the angular speed of Earth. Actually, I'm gonna do that down here. I'm gonna figure out because I'm gonna set the whole railroad tracks. I got a nice space down at the bottom of this page for some railroad tracks. Right. Angular speed of Earth. Angular speed of Earth is what's one way to couch it, guys? How fast is the Earth rotating? One revolution every day, right? Yeah. One revolution. Yeah, let's do that. One revolution every 24 hours, maybe. Right. I think if you like get way out in space, the fact that there's also going around the sun, it's something like 23.9 something hours, but we'll just call it 24 hours. Right? 24 hours. Right. Let's have some railroad tracks because I want to convert this into. Okay, we got revolutions per hour. We probably want the unit of what per what for angular velocity. radians per second, right? Radians per second, right? So yeah, let's get it. So how many radians in a revolution? 2 pi, 2 pi, right? So it's 2 pi rad in a rev. Okay, now we need to get the seconds. Ooh, 1 hour is 60 minutes. 1 minute is 60 seconds. Okay. Figure it out. What is 2 pi divided by all these things? 24 by 60 by 60. Okay. I'm looking at 0.0000727 radians per second. If you like, you can call that 7.27 times 10 to the negative 5 radians per second. Okay, right. There. There's how fast the Earth is rotating. Okay? There's 24 hours a day, right there. Okay. But in terms of radians per second, that's what that is. So it's a tiny number. If you're out in space, right? Maybe you'd be able to see. How about this? If you look at a clock and you look at the hour hand, the hour hand takes 12 hours to go around, right? The Earth takes 24 hours to go around once. So this is moving at like half the speed of the hour hand. Think of it that way, right? All right, but we don't want angular speed at the equator. We want linear speed at the equator. Guys, how do you get linear speed from angular speed? You need to know one more thing, which is what? Radius? Ah, right. Where's my Roosevelts? Do I have? One of my Roosevelts ran off. Well, I got 2 Roosevelts. How about that? Okay. Okay. So what if we're looking down from the top? Here's the North Pole here, and we're looking around like the curvature of the Earth. Here's the guy on the equator. Right, you guys see that? Ah, right. It's like further up. Right. So if you know how fast they are spinning, multiply by the radius of the Earth, that'll get you all the way to the equator. Ah, that'll give you the linear speed at the equator. So let's do linear speed at the equator is equal to angular speed for the entire Earth times the radius of the Earth. Okay. So it's going to be 7.27 times 10 to the negative 5. That's radians per second. Multiplied by. All right, now here's where what they say the radius of the Earth was 6.38 times. Now they said 10 to the 3 kilometers. Guys, 10 to the 3 kilometers. How do you go from kilometers to meters? Multiply by 1,000? Yeah. Okay. So if we got 10 to the 3 kilometers, that's 10 to the how many meters? 2. 3, 4, 5, 6. 3, 6. Ah, 6. There you go. Right. 3 plus 3, right? Right. It was power 3. We need 3 more. Right. Sure. 10, 10, 10. It's another 1,000. Right. And I was kind of crunched up there, but. Right. If you like, you could call it meters per radius because I mean it is the radius, right? All right. So anyway, how do you do it? Let's do 7.27 times 10 to the negative 5. That's radians per second. Gotta multiply that by 6.38 times 10 to the 6. That's the radius in meters, right? That's how many of these there are. Right, radius of the Earth. Right. Let's put it all together. I'm getting the speed is right. The number on my screen is showing well around the nearest whole number. It's like 464. Because that's 464. What? What's the unit? Meters per second. Right? Right? Because we did everything else based on SI units. I got meters here, I got radians, got meters per second. Okay. By the way, that's pretty close to 1,000 miles an hour. Right? Okay. Is this guy gonna fly off at like almost 500 meters per second? Like 1,000 miles an hour? It's gonna fly off? Well, maybe it depends on like what's the gravitational pull of the Earth. Right. Let's check out these other questions. Because this is a multi-part question, right? So we answered part A. Part B, what's the force needed to accelerate the person in a circle? Right. So let's switch perspectives here for part B. It's like here's this guy, right? He's on this curved path. Idea? Oh. Yeah. let's do free body diagram, FBD, free body diagram for this guy. There's two forces on him. There's two forces, right? What's one force? His weight, mg. What's the other force? The normal force, right? Now here's where I'm going to tell you something different from what I told you before. Haven't I always told you that the normal force just balances out the weight? I've always told you that, right? Right. Well, guess what? I've been lying the whole time. Ha 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 ha. Guess which force is actually a little bit bigger? The weight down or the normal force up? The weight down's a little bit bigger. The normal force up is not actually as much. I did a little bit exaggerated there. The weight down is more than the normal force up because this guy is not actually on a flat surface in equilibrium. He's actually rotating. He's actually moving on a curved path. What that means then is that there is a small centripetal force. Hey, is there a small centripetal force on all of us right now? Yeah, because we're moving on a curved path, like on a curve, like rotating Earth. Right? So I can think of it like this. The centripetal force is really the net force, which is the difference between those two forces, right? Maybe we can say this, like F net equals centripetal force, which is the weight down minus the normal force up, right? Again, like up until like last week, I always told you that these two balanced out, so there's zero net force if you're just standing at rest, right? But now I'm saying, well, that's not exactly true. We're going to see like how much it actually deviates, right? We're going to find out. Okay. So what force does it need? Oh, centripetal force. Could that be centripetal force is like mv squared over r? Right. Here, we're just going to go ahead and plug in what is that net force? What is it? Just for this question, part B. So it's like what force keeps them on its curved path, basically. And then we'll come back to like the rest of this later. All right. So centripetal force is, now they gave you a 97 kilogram person. Let's go to, let's do 97 kilograms. I don't know why they picked that. Let's say he's on the equator, which means he's going this many meters per second linear speed squared, and he's at the full radius of the Earth, 6.38 times 10 to the 6 meters we figured it was, right? So we converted kilometers to meters, we got that number. 6 million kilometers. 97 times 464 squared, all divided by 6.38 by 10 to the 6. I got grouped in parentheses, right? That's like 3.27. Guys, that's 3.27 what? What's the unit? How do you measure force? Newtons, right? Isn't that force? Those are newtons, right? Okay, so this guy at the equator, who's actually pretty heavy. That's actually a pretty heavy mass right there. Has a net force on him, which is not zero, right? It's actually about 3 newtons. Guys, 3 newtons, that's like this right here. Here's 3 newtons, right? Here's 3 newtons, right? Now, us up in Florida, we're at a higher latitude, so we don't get this full effect. We're not quite at the equator, right? Also, I think probably most of us are like less than this number of kilograms mass, right? So just kind of ballpark estimate. This difference right here, probably about 2 newtons or so, is the difference between your actual gravity force pulling you down and like the force reading on a scale. When you step on a scale, let's draw a little scale right here. When you step on a scale, that scale reading is not telling you exactly your weight. It's telling you actually the normal force. But you guys know that from elevator physics, right? Inside an elevator, it's all one, right? But actually, yes, same thing here. Suppose the scale says you weigh like so many pounds or something. Well, Earth's actually pulling you a little bit harder, but you're on a curved path that's rotating, right? So the amount you actually weigh is about this much more. So fun food for that right there. So normal force is not exactly the gravity force, but if you work out percentage, let's see what percentage is this. What's the percentage difference? Okay. What is 3.27 newtons compared to the full? This guy weighs like 970 newtons, right? 970 newtons he weighs, right? What is that? What's that divided by 970? Right. It's about 0.0034. You can call that 0.34%. Is that about a third of a percent? About a third of a percent? Okay. So the difference between your actual weight and the weight reading on the scale is like a third of a percent. So are you anywhere near being thrown off the Earth because of its rotation? No, like nowhere close. Okay. What else we got? Question C, what's the weight of the person? Well, here, I just answered that right here, didn't I? C, weight is mg, which is 97 times 10 is 970 newtons. Right, we've done plenty of those this year, right? You guys know how to get weight from mass, right? Okay. And then question D, what's the normal force on Earth that's the person's apparent weight? So if they step on the scale, right? Well, here's where I'm going to go back to this expression right here. I'm going to rearrange it and solve for the normal force, right? Right, is that okay? That's what we're going to do. So start with that. Maybe I could rearrange this type. So I'm going to get, from this, I'm going to get normal force is, okay, add that over, subtract that over, is weight minus the centripetal effect, sort of, right? So the normal force is, see this, we figured it was 970 newtons, right? Mass times gravity field. This centripetal effect, you can think of it that way, is like 3.27 newtons. Maybe if we round that to about 3 newtons, right? Is that about 967 newtons, right? So this guy on the equator steps on a scale, and the scale says, you weigh 967 newtons, right? Earth's actually pulling on them with 970 newtons, right? So it's not a huge difference, right? But there is a tiny difference there, right? Like I said, all right, yeah. But if anyone says that, well, why is it there? Oh, you know, I want to give you guys a little bit more trivia too, because here, do you guys know how long people have known that the Earth is round and what the size of the Earth is? What this? Hold on. Okay. All right. Do you guys know how long people have known how large the Earth is? People have known a long time the Earth is round, right? There's a story from ancient Greece. There's this guy named I always butcher his name. I'm going to call him Eratosthenes, something like that. Eratosthenes. I don't know. I can never say his name. Right? He was this Greek guy. He was actually down in like Egypt, right? So it's about right here, right? And there's like some town in Egypt that like one day every year the sun is directly overhead, so nothing ever has a shadow. You look straight down the well, and like, there's no shadows or anything. It looks real weird, right? I don't think that quite happens in the States. We're like too far north, right? But then he knew there was another town like so far north, and the distance was known between these two towns, and there was a shadow. So if you put a stick in the ground here, and you put a stick in the ground here, and the sun's like up here, like very, very far away, right? And it's like shining towards you, right? Then this stick will have a shadow, and it was like so many degrees, and it was like 2 degrees, right? This has none at all. And what you could do is you could back calculate, like, assuming the sun was very far away, which it is, right? You know what the angle is, what the distance is between these two cities. You can calculate the radius of the Earth, let's say the circumference of the Earth, right? Or what the size of the Earth is, right? People have actually known this for thousands of years, so pretty fun right there. So Earth is round, it's spinning, fun times. You guys ready for this lab? Ready for this lab? Right. So, like I told you guys before, right. About a week or so back, you guys did the turntable lab, kinematic motion we're looking at. You guys made some graphs. I graded this, gave it back to you guys, and printed on the back side is the lab we're going to do right now. Right. So you guys got turntables. You guys have mass slugs. I'm going to use Mr. Roosevelt right here. Right. And give this thing a spin. Right. Oh, guys, what force is... Oh, here's my third Roosevelt. Hide forever. Right. What force is holding those Roosevelts on the turntable right now? Friction, right? Friction, right? What if I spin this faster? Which one's going to fly off first? Yeah, the one on the outside. And then that guy. Oh, and that guy's real hard to move off, right? Do you guys think that how fast I have to spin it and where? Okay, obviously the radial location has something to do with it, right? Like, right? Do you think coefficient of friction between these two surfaces, like this coin material and this wood material, has something to do with how fast I have to spin it? Right? Because if it was like sandpaper, I could probably spin a little bit faster than the whole deal. Right? Right? So let's get a look here. Right? Give you guys a table. Your guys' goal today is to figure out what is the coefficient of friction, okay, between say like that turntable surface and a mass slug. Okay? So you guys got different trials. Here, I'll do an example trial with the guys. I'll call this trial 1. How about that? Right. Oh, I gave you guys a gravity field. Look at that, 980 centimeters per second squared. You guys have used that before for your Atwood lab. 980 centimeters per second squared, right? So we're doing something with centimeters today. What is the radial distance in centimeters? So I break out my ruler, I measure what is this distance in centimeters. Let's say I get 14 centimeters. Make up something a little bit different every class, right? Because 1 revolution, how many radians is that equal to? 2 pi. Okay, so I printed that number for you guys, but you guys know that. All right, what I want you guys to do as a procedure is spin this faster, faster, faster until the slug breaks friction and slides off. At that moment, maintain the angular speed, break out the stopwatch, and time how much time it takes for 1 revolution. Okay, is that so? You can figure out how much time does it take to go around once. Do that a few times, so you get an average. Let's say you come up with like 1.1 seconds, 1.05 seconds, and 1.15 seconds. I'm just making something up, right? So the average is like 1.10 or whatever the average is, right? Right. Can you figure out what is the angular speed if you know the time period? Is it just angular distance divided by time, right? Can I do, it tells you exactly right here what to do. 2 pi radians it went around for that revolution. And it did that in this many seconds. Is that like this many radians per second? That many radians per second that would be, right? Okay. And finally, going in for the wind here, there's this whole proof that I wrote above this last column to solve for coefficient of friction. I'll show you guys the larger version right here, right? Here we go. Free body diagram on the coin, 3 forces. Weight down, normal force up, which are balanced out. Well, you guys know now that they're actually off by about 0.3%, but that aside, let's just call them the same. And then friction force here. Friction force is providing centripetal force. Does this look a lot like that card turning question from earlier today that we started with? Right? Coefficient of friction times normal force. That's your friction force. It's allowed to be equal if it's at the point where it breaks friction, slides off. We're talking about static friction here. M omega squared R. Ooh, that's a little different from the car on the road, right? Turntable friction. Right? There's centripetal force. Right? Next step. We're gonna substitute weight for the normal force, just say those are balanced out. Right. Then, oh, here's where the mass cancels out. So I never had you guys record the mass. That's okay, it cancels out. But maybe that's not a huge surprise based on what you guys seen so far. Right. Then algebraic rearrangement. You can get the coefficient of friction. It's this expression right here. You guys see that? Okay. I did that for you guys, and that's exactly what it says to do right here. So last demo example, coefficient of friction is, I'm going to take my angular speed in radians per second. I'm going to square that. I'm going to multiply by the radial distance in centimeters. I'm going to divide that by Earth gravity, but in centimeters per second squared, which is the full 980. Now, one last thing. I'm about to hit enter. Guys, what is a reasonable coefficient of friction? Suppose you do this whole thing and you get like 75. Does 75 sound like a reasonable coefficient of friction? No. What about like 0.75? Does that sound reasonable? Yeah. That sounds reasonable, right? Coefficient of friction is what's the ratio of friction force to normal force. It's usually between 0 and 1, right? Oh, I got 0.47, 0.47. That definitely looks reasonable. Okay, so I'm happy with that. Can you guys knock out, do you guys think at least a couple rows by the end of class? All right, got some time here? All right, I'll walk around, help you guys out. When you guys get that, throw that in the grade tray, and I will give you guys some points. Points, physics points.